Hello. Oh, thank you. Hello, everyone. I'm Xie Min from Hong Kong University of Science and Technology. Welcome to my presentation. And in this presentation, I will briefly introduce our paper, Efficient K-regret query algorithm with restriction-free bound for any dimensionality. This is the outline of this presentation. We will go through introduction, problem definition, algorithm, experiment, and finally the conclusion. I will mainly focus on the motivation and the problem and briefly introduce the algorithm, the technical details, and the experimental evaluation. Let's start with the introduction. So a database system nowadays usually contains millions of tuples, and an end user might be just interested in only some of them. So it is very convenient if a database could provide some kind of operators that for an end user to obtain the tuples he is interested in. This is what we call the multi-criteria decision-making problem in the literature. So consider the following concrete scenario, Alice again. We assume that each car is characterized by two attributes, namely the horsepower and the mile per gallon. We use HP and MPG to denote it. And Alice will visit this car database and want to buy a car with very high horsepower and high mile per gallon. However, the problem is the car database can be very large and it contains a lot of car tuples. So it is impossible for Alice to go through the car tuples one by one. So a possible solution is that some representative cars are selected based on certain criteria. For example, the cars favored by Alice the most, and these cars are chosen and they are shown to Alice. Formally, we show cars based by considering Alice's preference. Assume that Alice's preference can be represented by a utility function. Based on this utility function, each car in the database is associated with a utility, which is a kind of score. And a high utility means that this car is favored by Alice. We have two goals in multi-criteria decision-making. The first one, we want little user effort. Since we do not require a user to specify his exact utility function, since it is difficult for him to explicitly specify it, which requires a lot of user effort. Secondly, we want a controllable output size in multi-criteria decision-making, since it is meaningless if millions of tuples are returned to the user. If Alice sees millions of car tuples, he can be overwhelmed. Some traditional query are proposed towards the multi-criteria decision-making. They are the top K query and the skyline query. However, these two representative queries cannot satisfy our two goals simultaneously. For example, in the top K query, the user is required to provide the exact utility function to the database system, which requires a lot of user effort. As for the skyline query, it does not have a controllable output size. In the worst case, all tuples in the database can be returned in the skyline query. Recently, we have a new query called the K-regret query was proposed. And intuitively, a K-regret query is just to find a set of representative tuples that minimize a criterion called the maximum regret ratio, and we denote it using MRR, the maximum regret ratio. And the K-regret query is pretty good. It integrates the merit of top K queries and the skyline queries. That is, it does not require the exact utility function from the user, and at the same time, only K tuples are returned in the K-regret query. Yes, but various algorithms were proposed for the K-regret query, but they have different kind of drawbacks. For example, some algorithms are just heuristic-based algorithms, and they cannot provide a provable upper bound, provable guarantee on the maximum regret ratio. Also, some algorithms might provide an invalid upper bound on the maximum regret ratio. I will briefly introduce what it means by invalid a little bit later. And although some other algorithms indeed provide some upper bound, but the upper bound is quite loose. It is not tight enough. And some other algorithms put some restriction. For example, it is only executable on some low-dimensional space, such as two-dimensional space, which means that each tuple is just associated with two attributes. It cannot be described by more attributes. And some algorithms are not that efficient. It is very sensitive to the dimensionality, which is the number of attributes that describe these tuples. And also, some empirical performance of some existing procedure is not that good. They produce a very large maximum regret ratio, which means that the solution set is of a poor quality. So motivated by this, we consider 4 requirements for evaluating an algorithm for the K-regret query. Firstly, the restriction-free bound requirement. I will talk more about it later. And the dimensionality requirement is very intuitively, the algorithm should be executable on dataset of any dimensionality. And efficiency requirement, the algorithm should be very efficient in practice. The quality requirement, which means that the maximum regret ratio of the set returned by the algorithm should be very small in practice. Let's look closer on the restriction-free bound requirement, what it means by restriction-free. Simply, it just means that there is no restriction on the upper bound on the maximum regret ratio of the set returned by the algorithm. Note that the maximum regret ratio itself is the value between 0 to 1. So if the upper bound is in the range between 0 to 1 for any setting, we say that the algorithm A satisfies this restriction-free bound requirement. Otherwise, if the upper bound is in the range between 0 to 1 in some restricted case, this algorithm cannot satisfy this requirement. Intuitively, an algorithm which does not satisfy the restriction-free bound requirement cannot give a theoretical upper bound in some cases and might give an invalid upper bound. For example, a bound greater than 1, it is meaningless in some other cases. So this is a summary of the existing algorithm for the K-regret query. We list the existing algorithm and we evaluate them using the 4 requirements we just mentioned. And some algorithms, such as the greedy, cannot give a theoretical upper bound. And for example, some algorithms are restricted to the 2-dimensional space when the data is only described by 2 attributes. And some algorithms are not very efficient. We may take an exponential time to execute. And also some algorithms are of poor quality. The maximum regret ratio they return is very large in practice. Motivated by this, the existing method cannot adjust the K-regret algorithm well since they cannot satisfy all 4 requirements simultaneously. So in this paper, we also studied the K-regret query, and we proposed a new algorithm called Sphere. And it has some attractive features, such as the Sphere algorithm has a restriction-free bound on the maximum regret ratio, and it is executable on dataset of any dimensionality. Besides, the upper bound on the maximum regret ratio of Sphere is asymptotically optimal. And it is really efficient. It adapts 20 times faster greedy strategy compared with the existing greedy algorithm for the K-regret query. Let's formally define this problem. Assume that the user happiness is measured by an unknown utility function, which can be regarded as the mapping. We denote it using F. And the utility of each tuple is simply denoted by FP. Without loss of generality, a user will want a tuple which maximizes the utility with respect to his utility function. The input to our problem is a tuple set with n tuples in a d-dimensional space. A d-dimensional space means that each tuple is described by d different attributes. And an integer k is used to constrain the output size. Consider a particular user with a certain utility function f. Since we restrict the output size to be at most k, it is very likely that there is a difference between the highest utility over all tuples in the database and the highest utility over the selected k tuples in the database. Consider the highest utility over all tuples in a database. It is kind of global maximum utility. And we denote it using the following notation. The capital P is just the whole database. And similarly, for the highest utility over the selected k tuple, it is kind of local maximum utility. And we describe it using the following notation, where S is our selection set, which just consists of k tuples. Based on this difference, we can define the regret ratio for each user. Given the set S and the utility function f, the regret ratio is simply defined based on the utility ratio between the global maximum utility and the local maximum utility. A user will be happy if the regret ratio is close to 0, which means that the highest utility over the selected k tuple is very close to the highest utility of the all tuples in a database. However, as we mentioned previously, it is difficult to obtain the exact utility function from a user. So we assume that there is a large function class which contains all utility functions. And a utility function of this user can be found in this large function class. The maximum regret ratio is then defined over this large function class. Given the set S and the function class FC, the maximum regret ratio can be just regarded as the worst case regret ratio or the largest regret ratio with respect to a utility function in this large function class. Formally, we started the k-regret query in this paper. Given an integer k, we want to find a set containing at most k tuples such that the maximum regret ratio is minimized. Intuitively, it quantifies how regretful a user is if he gets the best tuple among the selected k tuples, but not the best tuple among all tuples in the database. Consider our account application again. Different users might have different preference in their mind. One might think that horsepower is more important. The other might think that mile per gallon is more important. So a k-regret query on the database return at most k cars minimize the regret level for all possible users. That says no matter what exact preference the user has, there is a car in the selected set which is favored by the user the most. We briefly introduce our algorithm sphere, and it consists of 4 steps. The first step is the initialization step, which provides a baseline guarantee on the utility achieved by the point in our selected set. Secondly, we will construct some representative utility functions, and based on this utility function, we will find the points with very high utility and include those points in our solution set. Finally, we might insert some additional points using a greedy procedure with some efficient pruning strategy. The technical challenge is in step 2 and step 3, and the representative utility function construct in step 2 must be chosen very carefully so that the points we can determine in the third step will ensure that the utility achieved by the points in our selected set is very high, and it is very close to the global maximum utility. Theoretically, we can prove an upper bound on the maximum regret ratio of the set returned by our algorithm, and this bound is both restriction-free and asymptotically optimal. Let's briefly introduce the experiment. Our experimental setting, we conduct experiment on different kind of real data set of different dimensionality and data set size. And we compare the sphere algorithm over the state-of-the-art algorithm for K-query. And we studied different factors such as the parameter K in the K-query and the effect of dimensionality D and the effect of data set size. We measure the execution time and the maximum regret ratio returned by each algorithm. Here is a sample result on a household dataset, which is a 7-dimensional dataset with more than 1 million tuples. And we vary the parameter K in these experiments. And consider the left subfigure, which measures the maximum regret ratio. The smaller, the better. Our sphere algorithm, shown in the cross notation, achieve the smallest maximum regret ratio in most cases. And consider the right subfigure, which measures the running time. Our algorithm is very efficient, and it is much faster than some existing algorithms. It can return the solution set within 0.1 second. Let's conclude my presentation. We introduced the K-regret query, and we propose an efficient algorithm called sphere whose upper bound on the maximum regret ratio is both restriction-free and asymptotically optimal for any dimensionality. And we conduct experiments to show the superiority of our sphere algorithm. Thank you. Any question?
I just have to ask, what are the best 3 algorithms for K-regret?
Sorry?
What are the best 3 algorithms? You showed that table of algorithms, and it's an excellent way to, it's an excellent data set for you to apply your algorithm to, right?
Oh, sorry.
Can you show the table of algorithms?
Yes.
You could apply your own algorithm to this table to figure out which are the best algorithms. I'm being a little facetious, but you could apply your algorithm to this, right?
Okay.
To figure out which are the best 3 algorithms.
Yes. Yes.
Of course, yours is the best, right?
Yes, because we achieve all 4 requirements. Okay.
Could you expand a little bit on how Sphere provides the specific bound on the regret ratio? Just because I guess intuitively you would expect that if you chose the utility functions adversarially, you could have one that has, grows extremely fast, for example.
Do you mean that how to achieve the bound, some intuitive idea how to achieve the bound?
I guess in a couple of slides you had the big O of k to the negative.
Yeah, I see. Do you mean this one?
That one.
Yes. So it is related to the second step and the third step of our sphere algorithm. Since we choose some representative utility function and we find some tuple which really have good utility with those utility function. So what we are guaranteed here is that, although I'm not sure what your utility function is, I'm sure that there is some representative utility function which is very similar to your utility function. And the points we are chosen in the step 3, you will also satisfy with these points. Since the utility function, your utility function is very similar to some utility function we chosen in the second step.
Okay, thank you.
If you could go back to that table, that compares all these differences. So what makes your algorithm or your approach stand out is that you can support any dimensionality. Although in practice, my perception is that in terms of multi-criteria decision making, in most cases, you don't really expect the users will look at too many dimensions.
Yes, but those algorithms are just restricted to in 2-dimensional space. So although in practice dimension will not that large, but maybe 3 or 4. So those algorithms which only allow 2 attributes are not applicable in these cases.
Actually, it's okay, I think I'm loud enough. Actually, dimensionality would help your maximum regret ratio anyway, because as dimensionality increases, the scores of the tuples converge. So actually, dimensionality, as it may sound funny, I would assume improves your maximum regret ratio. Did you observe something like that in your experiments?
So, do you mean that when the dimensionality increase, the maximum regret ratio empirically will become larger or smaller for you?
Smaller, your quality will be better.
No, actually, because when you have more criterion, it is not always, it is more difficult